Chapter 10 Simple Linear Regression. This is one of the most important chapter of your quantitative methods module, and the chapter is pretty lengthy. So first we will look at what is the simple linear regression model. Then we look at various assumptions associated with the simple linear regression model. Then we conduct hypothesis test in the simple linear regression model. And then we will see how do we use the simple linear regression model to make predictions about a particular variable. Then at last, we will look at some functional forms of the simple linear regression. Second section, estimation of the simple linear regression model. Before understanding what a simple linear regression model is, let us understand why does the need arise for us to use the simple linear regression model. Analyst often wants to know whether one variable can be used to explain or predict the other variable or not. So for example, the analyst collects the data of the return on asset for 6 companies, and the analyst wants to know why does the ROA differ among the companies. He could either compare ROA of each companies. Say he compares ROA of company A with that of company B and figure out why is there a difference between the two ROAs. He can compare ROA of company D with ROA of company F and find out why is there a difference. Instead of comparing each company's ROA with other companies, a simple way is to compare ROA of each company with the arithmetic mean and try to figure out why is there a deviation, why is there a variation of ROA of each company from the arithmetic mean. So the analyst goal is to understand what drives the ROA, what explains the variation of each company's ROA from the arithmetic mean. So this is the variation that we are trying to explain. This formula is similar to that of variance, except that we don't divide by n minus 1. So we simply have the sum of squared deviation or sum of squared variation. So the analyst believes that the capex, that is the capital expenditure, can be used to explain the variation of ROA. So he collects the capex information of all the 6 companies and uses the capex to explain the variation of ROA. Here ROA is referred to as the explained variable. We also refer to it as the dependent variable and it is denoted by capital Y. Whereas capex, which is used to explain the variation of the dependent variable, is referred to as the explanatory variable or the independent variable and is denoted by capital X. And the variation that we are trying to explain, the variation of the dependent variable that we are trying to explain is referred to as the sum of squares total. Sometimes it is also referred to as the total sum of squares. So linear regression method is most often used for explaining the variation of the dependent variable. A common method to relate the dependent and the independent variable is through estimation of the linear relationship between them. And we use the linear regression method to estimate this linear relationship. If we have only one independent variable to explain the dependent variable, we refer to this as the simple linear regression. But if we have multiple independent variables, we refer to it as a multiple linear regression. An analyst is researching the relationship between the corporate earnings growth and the stock returns. Specifically, she is interested in whether the earnings revision are related with the stock price return in the same period. So she collects the data of the earnings per share revision and the stock price return for a sample of 100 companies. What are the dependent and the independent variables? So the analyst is using the earnings per share revision. She is using the earnings per share revision data to predict or to explain the stock returns. So independent variable is the earnings per share revision data and stock return is the dependent variable. In level 1, we will be studying the simple linear regression and multiple linear regression will be covered in level 2. So linear regression can be used to relate the two variables by assuming a linear relationship between them. Linear regression assumes a linear relationship among the two variables to explain or predict the dependent variable using the independent variable. And this is the linear regression model. This is the linear regression formula that we will be using to predict the dependent variable. Yi refers to the actual value of the dependent variable, and this is the predicted value of the dependent variable. This is indicated by y hat I, and this is the error term. So suppose the actual value of dependent variable is 8% and the value predicted by the linear regression model is say 6.5%. Then the difference between the actual term and the one predicted by the linear regression model will be our error term, which is 1.5%. B0 and B1 are referred to as the regression coefficient. These are calculated based on the population data. B0 is referred to as intercept and B1 is referred to as slope coefficient. But we know that it is not possible to collect and analyze the population data. That's why it becomes difficult to compute the intercept based on the population data and to compute the slope coefficient based on the population data. So this is the linear regression model based on the sample data, where everything else remains the same except for the regression coefficient. The regression coefficient are calculated based on the sample data, and these are indicated by b hat 0 and b hat 1. B hat 0 is an estimation of what the population intercept could be, and b hat 1 is an estimation of what the population slope coefficient could be. And this is the formula of the slope coefficient, the estimated slope coefficient, which equals to covariance between the dependent and the independent variable divided by the variance of the independent variable. The formula is very similar to that of the correlation. Correlation equals to the covariance between x and y divided by the standard deviation of x and standard deviation of y. The only difference is in the denominator, and this is the formula of estimated intercept, which equals to average of the dependent variable minus the b hat 1, the slope coefficient we calculated earlier, multiplied by average of the independent variable. Going forward, we will simply refer to this as the intercept and we will refer to this as the slope coefficient. Now let us calculate the intercept and the slope coefficient. So the slope coefficient equals to the covariance of xy divided by the variance of x. So covariance equals to 153.30 divided by n minus 1. So we have 6 observation, so denominator will be 5, and variance equals to 122.64 divided by n minus 1, which is 5. So we can also write this as 153.30 divided by 122.64. So the slope coefficient equals to 1.25. Now let us calculate the intercept. Intercept equals to the average of the dependent variable 12.5 plus the slope coefficient we calculated, which is 1.25 multiplied by average of the independent variable, 6.1. So the intercept is 4.875. Now how do we interpret what actually is the meaning of these regression coefficient? This was the linear regression model where the predicted value of the dependent variable equals to the intercept plus the slope coefficient multiplied by the observed value of the independent variable. The intercept implies that if the value of the independent variable is 0, then the value of the dependent variable will be equal to the intercept. So in our case, if the value of the independent variable is 0, then the predicted value of the dependent variable will be 4.875%. And the slope coefficient implies that for 1 unit increase in the independent variable, the dependent variable will increase by 1.25 units. So intercept is the value of the dependent variable, the predicted value of the dependent variable, if the value of the independent variable is 0. And the slope is the change in the dependent variable, change in the predicted value of the dependent variable for a 1 unit change in the independent variable. So we have calculated the intercept and the slope coefficient. So using the slope coefficient and the intercept, let us find out what is the value predicted by the linear regression model of the dependent variable. So these are the predicted value of the return on asset. So the linear regression model predicts that the return on asset for company A equals to the intercept, which is 4.875, plus the coefficient, the slope coefficient 1.25, multiplied by the value of the independent variable, which is 0.7. So the predicted value of the return on asset of company A equals to 5.750. So similarly, we can use the regression model to predict the dependent variable for any value of the independent variable. And these are the residuals, that is the difference between the actual value minus the predicted value. So an ideal linear regression model is the one which have the lowest possible errors. We want sum of all the errors to be as low as possible. But if you have a careful look at sum of all the errors, in a linear regression model, sum of all the errors will always be 0. If you remember from our previous chapters, where we studied the standard deviation, we have seen that sum of the deviations was always 0. So we looked at the sum of squared deviation. Similarly, in a linear regression model, sum of the errors will always be 0. That's why we look at sum of all the error terms squared. So an ideal linear regression model is the one which have the lowest possible sum of squared errors. So if we plot the data of the dependent variable and the independent variable, this is the scatter plot that we get. This is the regression line that we get, where the regression line represents the value that the dependent variable can take for a value of the independent variable. So this was the data point of the first company. That is, for a 0.7 capex, the ROA was 6%. But the value predicted by the linear regression model for a 0.7 capex was 5.25, which is represented by this linear regression model. So a regression line is the line which is fitted through the observation, and this line explains the value that the y can take for any value of x. So the regression line represents the predicted value of the dependent variable for any value of x. So if the independent variable is this, then the predicted value of the dependent variable is this. So these are the predicted values and these are the actual values of the dependent variable. And the difference between the actual value and the predicted value is referred to as the residual. So a regression line is the one which minimizes the sum of the squared residuals. So even in the previous slide, we have said that the ideal regression model or an ideal regression line is the one which minimizes the sum of squared residuals. The sum of squared residuals is also known as the sum of squares error or the residual sum of squares. So this is the formula of the sum of squares error which we are trying to minimize. This is the error term. We take square of the error terms and we add all the error terms squared. So we want the linear regression model to minimize the sum of squares error as much as possible. We have two types of regression. One is the cross-sectional regression and another one is the time series regression. So an example of cross-sectional regression could be, suppose I collect the earnings per share data of various companies, say company A, B, C, D and so on. This EPS data is for the past 1 year. And I also collect the data of stock returns for the past 1 year of all the companies. I want to forecast what the stock returns could be for each company using the earnings per share. This is an example of cross-sectional regression, which involves many observations of X and Y for the same time period. And observations could come from different companies, asset, entities, etc. An example of time series regression could be, suppose I want to forecast what could be the stock return of company A. So the independent variable is the earnings per share. I collect, say, yearly earnings per share of the company A for past 10 years. So I have earnings per share of company A for past 10 years and I also have the stock return of company A for the past 10 years. So this is an example of time series regression where we use many observations from different time periods for the same company, asset, entity or funds. An analyst is exploring the relationship between a company's net profit margin and the research and development expenditure. The analyst collects data for an industry and he calculates the ratio of the R&D expenditures to revenues and the net profit margin. And he collects the data for 8 companies. This is an example of cross-sectional regression where the dependent variable is the net profit margin and the independent variable is the ratio of R&D expenditure to revenue. The analyst wants to explain the net profit margin's variation by using the variation observed in the company's R&D expenditure. So this is the dependent variable and this is the independent variable. We are required to calculate the slope coefficient, the intercept. We are required to show how the linear regression model is represented and what is the pairwise correlation between the two variables. So first let us enter the data into the calculator. We will be using the data function and the statistic function. So press second and then press data. So in x01, you first enter 8, press the down arrow key, then press 4 in the y01 column. Similarly, you enter all the data. And after you have entered the last data, that is the y08, you press second and then press 8. This shows up the statistic function. So the formula of the slope coefficient equals to the covariance divided by the variance. The calculator does not directly provide you with the covariance. We need to find the covariance from the correlation data and the standard deviation data. So you press down arrow key and the standard deviation of x equals to 2.07. You press down arrow key until you find the standard deviation of y, which is 3.19. Be careful that we have two standard deviation. One is represented by Sx, another one is represented by sigma x. Sx represents the sample standard deviation whereas sigma x represents the population standard deviation. Because we are using the sample data, we are concerned with the sample standard deviation. And again press down arrow key until you find the correlation, which is negative 0.842. So correlation equals to covariance divided by standard deviation of x and standard deviation of y. Rearranging the formula, covariance equals to the correlation, which is negative 0.842 multiplied by 2.07 multiplied by 3.19. So the covariance that we get is 5.57. So the covariance equal to 5.57 and the variance equals to 2.07 squared, which is 4.28. The covariance is negative and the slope coefficient that we get is negative 1.3. A slope coefficient of negative 1.3 implies that for 1 unit increase in the independent variable, the dependent variable will decrease by 1.3 units. So this is the slope coefficient. Now let us calculate the intercept. Intercept equals to average of the dependent variable. So using the statistic function, press down arrow key until you find y bar. So the y bar is 6.75 plus the slope coefficient multiplied by the average of the independent variable. So the independent variable's average is represented by x bar, which is 7.5. So the intercept comes out to be 16.5. Now let us see how does the linear regression model looks like. So the estimated value of the dependent variable equals to intercept, which is 16.5 plus the slope coefficient multiplied by the value of independent variable. And we have already find out what is the correlation between the two variables. The correlation was negative 0.842. Now let us look at some of the assumptions made by the linear regression model. The simple linear regression model produces valid results when the following key assumptions are met. The first assumption it makes is that the two variables, the dependent and the independent variable, have linear relationship. But if the two variables relationship deviates significantly from linear relationship, then the results produced by this model will be incorrect. The second assumption is of homoscedasticity, which means that the variance of residuals should be same across all the observations. The third assumption is that the pairs of x and y should be independent of each other. And the fourth assumption is the residual terms, that is, the error terms should be normally distributed. We will look at each of the assumption in detail over the next few slides. Let us look at the first assumption, which is linearity. The simple linear regression model produces valid results when the two variables have linear relationship. Linear relationship implies that for 1 unit increase or decrease in the independent variable, the dependent variable changes by the same unit. For example, if the independent variable increases by 1 unit, then the dependent variable is said to increase by 3 units. So, if the independent variable increases by 2 units, the dependent variable should increase by 6 units. Then in such case, we refer to the relationship as a linear relationship. Although practically it is not possible for two variables to have such perfect linear relationship, the model can still be used even when the two variables have approximately or roughly a linear relationship. The model still gives valid results. But the model may produce invalid results when the two variables relationship completely deviates from linearity. So in the following example, the two variables follow a non-linear relationship, and this is the regression line that we have forecasted. So the regression model underestimates the dependent variable for certain values of y, and it overestimates the dependent variable for certain values of x. So for such non-linear relationship, the simple linear regression model is not that useful. Another important observation is that if the residual, that is, if the error term exhibits certain pattern when plotted against the independent variable, then this implies that the two variables are not linearly related. So using the same data, suppose we plot the residual, that is the difference between actual value and the predicted value. If we plot the residual against the independent variable, if we see certain pattern, as we can see in this case, then this implies that the independent variable and the dependent variable have a non-linear relationship. Ideally, we want the residual patterns to be random. This implies that there exists a linear relationship between the two variables. Another implication of the linearity assumption is that for two variables, that is, for the dependent and the independent variable to have a linear relationship, the independent variable should not be random. If the independent variable is random, then it implies that there is no linear relationship between the two variables. The second assumption that the simple linear regression model makes is homoscedasticity. When variance of the residual term, when variance of the error term is approximately same across all the observation, then this is referred to as the homoscedasticity. And for the simple linear regression model to provide accurate results or to provide correct results, it is necessary that the variance is approximately same across the observation. If variance differs significantly across the observation, we refer to this as heteroscedasticity. There is no formula to calculate the variance of residuals. Just by looking at the residual plot, we can figure out whether the variance is similar or different across all the observation. So let us take an example. Suppose we are conducting a time series regression on the short-term interest rate. So the dependent variable is the short-term interest rate and the independent variable is the inflation rate. The short-term interest rate of a country and the inflation rate of a country. We collect 16 yearly short-term rates and 16 yearly inflation rates. So we have data for 16 years, where for the first 8 years, the interest rates were normal. But for the last 8 years, the interest rates were kept very low. So this is how the scatter plot looks like. So it is clearly visible that during the first 8 years, the interest rates were pretty normal. But during the last 8 years, the interest rates were kept very low. And this is the regression line that we forecasted. Now let us see how does the residual plot looks like. So when we plot all the residual terms, the 16 residual terms on a graph, this is how the residual term looks like. So on the x-axis we have year and on the y-axis we have the residual terms. So as you can see that during the first 8 years, the residual or the error terms are pretty low. But for the last 8 years, the error term is pretty high. So it is clearly visible that the variance of the residual term is not even approximately same across all the years. So the variance across the first 8 years looks approximately the same, whereas the variance across the last 8 years, the last 8 observation looks approximately the same. But the variance between the two different periods are completely different. So as far as residuals are concerned, we have two different regimes. The first regime where the variance is low and the second regime where the variance is high. So when variance of the residual term differs across the observation, it indicates the existence of distinct regimes as far as variance of residual terms is concerned. So using only a single simple linear regression model across all the observation, that is across two regimes whose variances are different. So using a single model might yield incorrect results. Hence, we should use different models for different regimes. This ensures that the model gives valid results. So, for each regime having approximately the same variance of residual, it is advised that we use a single regression model for each regime. So, for the first 8 years, where variance of residual is approximately same across all the 8 years, we use one linear regression model, and for the last 8 years, when the variance of the residual is approximately the same, we use another regression model. This way, we satisfy the assumption of homoscedasticity, and the simple linear regression model gives us accurate results. The third assumption that the simple linear regression model makes is of the independence. For the model to give valid results, it is necessary that the observation pairs are uncorrelated. Continuing with our previous example, where the dependent variable was return on asset and the independent variable was the capex. Suppose we collect data of 4 companies. So we have Y1, Y2, Y3 and Y4, and X1, X2, X3 and X4. And these are the observation pairs Y1, X1, Y2, X2, Y3, X3 and Y4, X4. So, for the model, that is, for the linear regression model to give correct results, it is necessary for the pairs to be independent of each other. By independent, we mean that when we plot these pairs on a graph, when we look at the scatter plot, the observation should not exhibit any pattern. So, when there is a correlation between the observation pairs, we refer to this as autocorrelation. And when there is autocorrelation between the observation pairs, it also implies that the residual terms are also correlated. So let us take an example where we conduct a time series regression on the quarterly revenue of a company. So the dependent variable is the quarterly revenue and the independent variable is time, that is each quarter. We collect the data of past 40 quarters of a particular company. And when we plot the 40 observational pairs on a graph, this is how the scatter plot looks like. We can clearly see that the observation pairs are exhibiting some pattern. During the first, second and the fourth quarter of every year, the quarterly revenues are low. But during the third quarter of every year, the quarterly revenue increases significantly. This implies that the observation pairs are not independent. There exists autocorrelation between the observation pairs. So when there is autocorrelation between the observation pairs, the model that we have forecasted does not predict the dependent variable accurately. So this is the regression line or the regression model that we have predicted. We can see that the actual value of the dependent variable is far away from the predicted value. Similarly, for all the third quarters, the actual value is very different from the predicted value. So, when there is autocorrelation present between the observation pairs, that is, when the observation pairs exhibit certain pattern, then the model does not do a good job of predicting the dependent variable. So, this is the residual plot. So, when there is autocorrelation present, even the residuals exhibit certain pattern, which is clearly visible over here. During the third quarter, the residual shoots up significantly and comes down during the next quarter. This pattern is seen across 40 quarters. So it is necessary for this assumption to be met so that the model gives us accurate results. For the linear regression model to give correct results, the residuals should be normally distributed. Now, having said that, it is not necessary for the population data of the two variables to be normally distributed. Even if the two variables have a population data which is not normally distributed, this does not violate the normality assumption. This assumption only requires the residual terms to be normally distributed. And according to asymptotic theory, when the sample sizes are large enough, it is usually found that the residual terms are normally distributed. So when the sample size are large enough, it is safe to assume that the residual terms are normally distributed. Let us look at the following example, where the analyst is investigating a company's revenue and estimates a simple linear time series regression by regressing the revenues against time. So the dependent variable is revenues and the independent variable is time, where the data is measured in years. We have data for the past 15 years. That is, our sample size is 15. The analyst plots the company's observed revenue and the estimated regression line as shown in Exhibit 17. She also plots the residual from the regression model as shown in Exhibit 18. So this is the scatter plot of the observation pairs and this is the scatter plot of residuals. So based on Exhibit 17 and 18, describe which assumption of the simple linear regression is the analyst model violating. The first assumption is linearity. From Exhibit 17, it is visible that the dependent variable and the independent variable have a non-linear relationship. This can also be confirmed by looking at the residual plot. When the residuals exhibit certain pattern, which they are exhibiting in this case, when the residuals are exhibiting certain pattern, it implies that there is a non-linear relationship between the two variables. So the first assumption is violated. The second assumption is of homoscedasticity. So from the residual plot, it is visible that the variance of the residual term for this regime is different from the variance of residual term for this regime. So there are two distinct regimes as far as the variance of residual term is concerned. So we can conclude that the variance is not similar across all the observation. Hence, the second assumption is also violated. The third assumption, which is independence. So, when there is autocorrelation present between the observation pairs, even the residual terms are correlated. That is, even the residual terms exhibit certain pattern. Even in this case, the residuals are exhibiting certain pattern. So we can conclude that even the third assumption is violated. And the fourth assumption is normality. So according to asymptotic theory, it is safe to assume that if the sample size is 30 or greater, then the residuals exhibit a normal distribution. But in this case, we have a sample size of 15 observation. Then there is very high probability that the residuals may not be exhibiting a normal distribution. So even the fourth assumption is violated. So all the four assumptions of the simple linear regression is violated in this case. After looking at the simple linear regression model and what are the assumptions that the model makes, we move our focus to the following. In this section, we will be covering the analysis of variance and the measures of goodness of fit. Under measures of goodness of fit, we will be looking at three main measures: the coefficient of determination, the F statistic, and the standard error of estimate. We started this chapter by asking ourselves a question, that what drives the dependent variable? What drives the variation, or what explains the variation of the dependent variable? So we calculated the sum of squares total, which is the total variation of the dependent variable. So it was summation of value of the dependent variable minus the average value of the dependent variable squared. We were concerned with what explains this total variation. So we chose an independent variable which we believed could explain this variation. So using a linear regression model, we tried to explain this variation. Now let us see how effective has the linear regression model been in explaining this total variation. This is the scatter plot of the dependent and the independent variable. So let us consider this data point over here. This is the actual value of the dependent variable, and this is the average value. We are concerned with explaining this deviation, which is the difference between actual value minus the average value. So out of the total variation that we want to explain, this much variation is explained by the linear regression model, and this much variation still remains unexplained. So of the total variation, we were able to explain this much variation, which is y hat, that is the predicted value minus the average value, and this much variation still remains unexplained, which is the actual value minus the predicted value. This is nothing but the error term. So we call this as the total variation. We refer to this as the explained variation and this as the unexplained variation. The total variation is nothing but the sum of squares total. The explained variation, we call it as the sum of squares regression, and the unexplained variation, we refer to it as the sum of squared errors. So if you remember, an ideal linear regression model is the one which minimizes the sum of squared errors. So the sum of squares total equals to the sum of squares regression plus the sum of squared errors. So the sum of squares total was summation of value of the dependent variable minus the average value squared, and the sum of squares regression equals to summation of the predicted value of the dependent variable minus the average value of the dependent variable squared, and the sum of squared error equals to summation of actual value minus the predicted value squared, and this is actually y hat and not y bar. So total variation equals to the explained variation plus the unexplained variation. An ideal model is the one which have the lowest possible unexplained variation. So continuing with our previous example of ROA and CAPEX, let us calculate the total variation, the explained variation and the unexplained variation. Total variation is yi minus y bar squared. Explained variation is y hat minus y bar squared, and the unexplained variation is yi minus y hat squared. So let us calculate it for all the 6 companies, and we get the total variation, explained variation and the unexplained variation. So the total variation is 239.50. The explained variation is 191.63 and the unexplained variation is 47.88. So after having calculated the total variation, explained variation and the unexplained variation, how do we know whether this explained variation is enough or not? Whether the linear regression model does a good job of explaining the total variation or not? So to evaluate whether the linear regression model did a good job of explaining the total variation or not, we look at the measures of goodness of fit. Measures of goodness of fit evaluates how well the regression model fits the data, that is, how well the independent variable explains the dependent variable. The first measure is the coefficient of determination, which is represented by r square. The coefficient of determination equals to sum of squares regression divided by sum of squares total, which is explained variation divided by the total variation. So in the previous example, the explained variation was 191.63 and the total variation was 239.50. The coefficient of determination comes out to be 80.01%. This means that 80% of the total variation is explained by the independent variable, which is pretty good. And in a simple linear regression, the square of the correlation equals to the coefficient of determination. So if you remember the correlation between ROA and the CAPEX, the correlation between the two variable was 0.8945. positive. And if we take the square of this, we get 0.8001, which is the same as coefficient of determination. But this happens only in a simple linear regression. In a multiple linear regression, the square of the correlation not equals to the coefficient of determination. The second measure of the goodness of fit is the F statistic. So the regression model that we have constructed had two regression coefficient, the B hat 0, which is the intercept, and B hat 1, the slope coefficient. These regression coefficient were based on a sample data. So we want to conduct a hypothesis test specifically about the slope coefficient, the population slope coefficient. We want to know whether the population slope coefficient is 0 or whether it is different than 0. We conduct this hypothesis test using the sample slope coefficient. We ideally want the slope coefficient, the population slope coefficient, to be different than 0. A population slope coefficient different than 0 implies that the independent variable does a good job of explaining the dependent variable, whereas a population slope coefficient of 0 implies that the independent variable is not a good explanatory variable. F statistic is used to test whether all the population slope coefficient in a regression are equal to 0 or not. In a multiple regression, we have multiple slopes because we have multiple independent variables. But in a simple linear regression, as we have only one independent variable, we have only one slope. So in a simple linear regression where we have only one independent variable, this is how the hypothesis is stated. We ideally want to reject the null hypothesis. Until now, what we have seen is that whenever the hypothesis is stated in such a way, it implies that it is a two-tailed test. But here, it is always a right-tailed test. Even though the hypothesis is stated in such manner, it is always a right-tailed test. So suppose this is the distribution of the F statistic, and this is the critical value, or we call it as the F value. If the F statistic is greater than the critical value, we reject the null hypothesis. And higher the F stat implies better the explaining power of the independent variable. So in this hypothesis test, we want to test whether the population slope coefficient is equal to 0 or is different than 0. And this is the formula of the test statistic. F equals to the mean squared regression divided by the mean squared error. The mean squared regression equals to sum of squared residuals, that is the explained variation, divided by k. K refers to number of slope coefficient. So in a simple linear regression, k will always be equals to 1. So the mean squared regression in a simple linear regression is the same as the sum of squared regression. The mean squared error equals to sum of squared error, which is the unexplained variation, divided by n minus k minus 1, which is as good as n minus 2. So you need to remember the formula of the test statistic as well as the formula of mean squared regression and mean squared error. This test statistic follows F distribution, and this is the degrees of freedom. We have 2 degrees of freedom. We will use the 2 degrees of freedom to find out the F value. Most probably on your exam, you will be provided with the F value, that is the critical value, and you will be required to calculate the F stat and then compare it with the F value. The third measure is the standard error of estimate. So standard error of estimate is nothing but the standard deviation. So just like the standard deviation tells us that on an average, how much does each observation differs from the average value, the standard error of estimate tells us on an average how much does each variable, that is each predicted variable, differs from the actual value. Standard error of estimate tells us the average deviation of the predicted value of the dependent variable from the observed or the actual value of the dependent variable. So we want the standard error of estimate to be as low as possible. A lower standard error of estimate implies that the model does a good job of explaining the dependent variable. Now, how do we calculate the standard error of estimate? Just like the normal formula that we use to calculate the standard deviation, which is yi, that is observation minus the average value squared divided by n minus 1. This is the sample standard deviation. Similarly, standard error of estimate equals to the square root of deviation of each observation from the predicted value squared divided by n minus k minus 1. So this is nothing but the root of mean squared error. The standard error of estimate is the root of mean squared error, and we want this to be as low as possible. Now let us look at the ANOVA table, which is the analysis of variance table. This table summarizes everything that we have studied until now. This table gives us the sum of squares regression, sum of squares error, and the sum of squares total. These are the degrees of freedom that we use to calculate the mean squares. That is, this is nothing but the denominator of the mean squares. So the mean square regression is sum of squares regression divided by 1. The mean squared error is sum of squares regression by n minus 2. And sum of squares total divided by n minus 1. This is nothing but the variance of the dependent variable. The ANOVA table also specifies the F statistic. Let us solve the following example. Julie Moon is an energy analyst examining electricity, oil, and natural gas consumption. She runs a simple regression explaining the variation in the energy consumption as a function of temperature. So the dependent variable is the energy consumption and the independent variable is the temperature. The total variation is 140.58. The explained variation is 60.16 and the sample size is 60. The coefficient of determination equals to the explained variation, which is 60.16, divided by the total variation 140.58. So the R square that we get is 47.29%. The second question is to calculate the F statistic of the test. F statistic equals to mean squared regression divided by the mean squared error. The mean squared regression is nothing but sum of squares regression divided by 1, and mean squared error is sum of squares error divided by n minus 2. Sum of squares error is nothing but the explained variation, which is 60.16, divided by sum of squares error is 140.58 minus 60.16, which is 80.42 divided by 58. So the F statistic that we get is 43.3082. The third question is to calculate the sample standard deviation of the dependent variable. So the sample standard deviation of the dependent variable equals to, as we have seen in the ANOVA table, the variance is sum of squares total divided by n minus 1. And if we take the square root of this, we get the standard deviation. So sum of squares total is 140.58 divided by 59. We take square root of this. The sample standard deviation is 1.544. I want you to solve this question for yourself. This is pretty easy and straightforward. So if you have solved the question, the answer to question 1 is 23.52%. The answer to question 2 is the standard error of estimate is the root of mean squared error, that is the root of 19.1180. So the standard error of estimate equals to 4.3724. And the third question is that at a 5% level of significance, do we reject the null hypothesis of the slope coefficient equal to 0 if the critical f value is 3.938? So the f statistic equals to the mean squared regression divided by the mean squared error. So the f statistic that we get is 30.1364. So this is the f distribution and this is the critical value 3.938. The f statistic lies far beyond this critical value. So we reject the null hypothesis and conclude that the population slope coefficient is significantly different than 0. This is a pretty straightforward question. I want you to solve this question for yourself. The answer to question 11 is 23.8. The answer to question 12 is 92.437%. Answer to question 13 is that the f statistic conducts the hypothesis test whether all the slope coefficients are equal to 0 or not. Question 14 is an interesting one. Here we are not given with the f critical value against which we can compare the f statistic and conclude whether we want to accept or reject the null hypothesis. Here we are given with the p value. So if you remember from our previous chapter, that p value refers to number of observations that lie below the f statistic, the percentage of observations that lie below the f statistic. Suppose this is how an f statistic looks like. So the p value, which is 0.00904, implies that 0.904% of the observation lie below the f statistic and the significance level is 5%. So the critical value lies somewhere over here where 5% of the observation lie below the critical value. So comparing the p value with the significance level, we conclude that we reject the null hypothesis and come to a conclusion that the slope coefficient is significantly different from 0. And the standard error of estimate is 1.549. So we have constructed the linear regression model using the sample regression coefficient. We use the sample intercept and the sample slope coefficient. In this section, we will be conducting hypothesis test concerning the population regression coefficient. First, we will conduct the hypothesis test concerning the population slope coefficient. Then, we will conduct hypothesis test concerning the population intercept. We have seen the f statistic to conduct the hypothesis test concerning the slope coefficient. But f statistic is often used when we have multiple slope coefficient. It is used in multiple linear regression. But in case of simple linear regression, when we have only one slope coefficient, we often use t statistic instead of f statistic. And while conducting the hypothesis test concerning the slope coefficient, we are most interested in testing whether the population slope coefficient, whether it is significantly different from 0 or not. And the hypothesis is, the alternative hypothesis states that the population slope coefficient equals to 0 and the alternative hypothesis is population slope coefficient not equals to 0. We ideally want to reject the null hypothesis. And unlike f statistic, which was a right tail test, this is a two-tailed test. So here we will have two different critical values. And if the t-stat that we calculate falls within this range, then we fail to reject the null hypothesis. But if the t-stat falls outside the critical value, then we reject the null hypothesis. A slope coefficient significantly different from 0. A population slope coefficient significantly different from 0 implies that there is a significant relationship between the two variables, and the independent variable does a good job of explaining the dependent variable. So here we are conducting hypothesis test concerning the population slope coefficient, and instead of using f-stat, we use t-stat. The probability distribution that the test statistic follow is t distribution, and this is the degree of freedom that we use to compute the critical value. The test statistic formula is the sample slope coefficient minus the hypothesized value of the population slope coefficient. So the hypothesized value of the population slope coefficient is represented by capital B subscript 1, and this is usually 0, divided by the standard error of the slope coefficient, and the formula is standard error of estimate divided by root of the summation of independent variables deviation squared. You need to remember the formula of the standard error of slope coefficient as well as the t statistic. This is referred to as the standard error of slope coefficient, and this is the standard error of estimate. So it doesn't matter if we use t-stat or f-stat to conduct the hypothesis test concerning the population slope coefficient. Both the t-stat and the f-stat will give us the same conclusion whether to reject or accept the null hypothesis. Even though the t-stat value might be different than the f-stat value, but the conclusion will be the same. There are some important observations about the test statistic of the slope coefficient. The t-statistic of the slope coefficient that we calculate equals to the t-statistic of the pairwise correlation. So if you remember the parametric test of the population correlation, the t-statistic of the sample correlation that we calculated equals to the t-statistic of the slope coefficient. Both the values will be the same, and the t-statistic of slope coefficient squared equals to the f-statistic that we have seen previously. So the t-statistic squared equals to the f-statistic. And if in the exam you get a question saying hypothesis wanting to test whether there exists one-to-one relationship between the dependent and the independent variable, it implies that the hypothesis is concerned about whether the slope coefficient is equal to 1 or not. Let us solve the following question. An analyst is interested in interpreting the results and performing the test of hypothesis for the market model estimation that regresses the daily return of the ABC stock on the daily return of the EAA equity index. He has generated the regression results as follows. So here the daily return of the ABC stock is regressed on the daily return of EAA equity index, meaning daily return of the ABC stock is the dependent variable and daily return of the EAA equity index is the independent variable. So we have the standard error of estimate, the standard deviation of the dependent variable, standard deviation of independent variable, the sample size, and these are the coefficient. If the critical t values are plus minus 1.96, then is the slope coefficient different from 0? So the null hypothesis here is the population slope coefficient equals to 0, and the alternative hypothesis is population slope coefficient not equal to 0. This is the sample slope coefficient that we have calculated. Using this sample slope coefficient, we need to test whether our hypothesis is correct or incorrect. So let us find out the t-statistic. T-statistic equals to the sample slope coefficient minus the hypothesized value of the population slope coefficient, which is represented by capital B1, divided by the standard deviation of the slope coefficient. So first let us find out the standard deviation of the slope coefficient, which equals to the standard error of estimate divided by the root of summation of deviation squared of the independent variable. So the standard error of estimate is 1.26 units divided by, we can derive the denominator using the standard deviation of the independent variable. The standard deviation of the independent variable equals to root of summation xi minus x bar square divided by n minus 1, which equals to 0.7. Now let us take the square of both of the variables. So we have summation xi minus x bar square divided by n minus 1 is 1199 and we get 0.49. Now rearranging the equation, we get the figure as 587.51. So this figure is 587.51. We take the square root of this and the standard deviation of the slope coefficient equals to 0.051983. So the t statistic equals to 0.982 minus 0 divided by 0.051983. The t stat equals to 18.907. So the critical values are plus minus 1.96. So at this level of critical value, we reject the null hypothesis and conclude that the population slope coefficient may be different than 0. And the fifth question hypothesizes whether the slope coefficient is different from 1 or not. So the t stat that we get here is negative 0.3463. So here we reject the null hypothesis and conclude that the population slope coefficient may be equal to 1. Now let us conduct hypothesis test of the population slope coefficient when the independent variable is an indicator variable. It is possible that the independent variable could be an indicator variable. We also refer to it as the dummy variable. Indicator variable can take only two values. It can either be 0 or 1. Let us understand this through an example. Suppose an analyst wants to regress the monthly stock return of a company on whether the company makes earnings announcement or not. So the analyst is interested in knowing what is the monthly stock return when company makes any earnings announcement and what is the monthly stock return when the company don't make any earnings announcement. So this is the dependent variable. This is the independent variable. The analyst collects data for the past 30 months. He collects monthly stock returns for the past 30 months and he also collects the data for the past 30 months on whether earnings announcement were made or not in each month. And this is the scatter plot of the monthly returns against the time. These data points, that is the data points in dark green shade, represents the stock return for the months when there were no earnings announcement. And this light shaded data points indicates returns for the months when earnings announcement were made. So by visually looking at the scatter plot, we can see that whenever earnings announcement were made, in that month the stock return has increased significantly. In the 5th month, in the 10th month and so on, when earnings announcement were made, the stock returns are significantly above the remaining data points. So we can say that there is some relationship between earnings announcement and the stock's monthly return. So the analyst forecasted a linear regression model and these are the result. And the regression model is the forecasted value of the dependent variable equals to 0.5629 plus 1.2098 multiplied by the independent variable's value. Here, the independent variable's value can either be 1 or 0. When any earnings announcement are made, the value that the independent variable take is 1, and whenever there is no earnings announcement, the value will be 0. By visually inspecting the scatter plot, we can conclude that there is some relationship between the monthly stock returns and the earnings announcement, which is the indicator variable. And this relationship is quantified by this regression model, which tells us that whenever any earnings announcement are made, the stock return increases by 1.2098%. But this slope coefficient of the independent variable is based on a sample data. So we want to conduct a hypothesis test on the population slope coefficient of the indicator variable. We want to know whether actually any relationship exists between the indicator variable and the dependent variable or not. So the null hypothesis is the population slope coefficient equal to 0. Alternative hypothesis is population slope coefficient not equal to 0. The t-stat equals to the sample slope coefficient minus the hypothesized value, which is 0, divided by the standard deviation of the slope coefficient or the standard error of the slope coefficient. So the sample slope coefficient is 1.2098 minus 0 divided by the standard error is 0.1158, and the test stat that we get is 10.4435, which is already given in the table. So against a 5% level of significance, when the critical value is 2.04, we reject the null hypothesis and conclude that the population slope coefficient is different from 0. So yes, there is a relationship between the indicator variable and the dependent variable. We can also test whether the slope coefficient of the indicator variable is significantly different from 0 or not by conducting the test of differences in the population means of the dependent variable. The two populations here are the returns for the earnings announcement month, and the second population is the returns for the non-earnings announcement month. So by conducting the test of the differences in the population mean, we can conclude that whether the slope coefficient of the indicator variable is different from 0 or not. And this is the hypothesis result, where the population 1, which is return for earnings announcement month, have 7 observations, and the population 2, the return for non-earnings announcement month, have 23 observation. And this is the mean of population 1, and this is the mean of population 2. And this is the difference in mean. So we conduct hypothesis test to check whether the differences in the population mean is equal to 0 or different than 0. So the null hypothesis is population mean 1 equal to population mean 2. Alternative hypothesis is population mean 1 not equal to population mean 2. Accepting the null hypothesis indicates that the stock return is not influenced by whether the earnings announcement is made or not, which implies that the indicator variable does not explain the dependent variable. There is no significant relationship between them, and hence the slope coefficient should be equal to 0. But if we accept the alternative hypothesis, it implies that the indicator variable does a good job of explaining the dependent variable, and the slope coefficient, the population slope coefficient, should be different than 0. So the t-stat that we get is 10.4435, and with the 5% level of significance, when we have this critical value, we reject the null hypothesis and conclude that the two population mean are different, which implies that the population slope coefficient should be different than 0. There are few observations here that the t-stat is same for both the test. in the previous test that we conducted and in this test, the t-stat is the same. The intercept in the regression model, which was 0.5629, is the same as the mean return for the non-earnings announcement month, and the slope is the same as the difference in mean. So we can also conduct the hypothesis test of slope coefficient using the test of differences in the population mean. Now let us conduct the hypothesis test on the population intercept. Here we want to test whether the population intercept is a specific value or not. Unlike slope coefficient, where we were interested in testing whether the population slope coefficient equals to 0 or whether it is different from 0. But in population intercept, we hypothesize the population intercept against a specific value. Here we conduct hypothesis test concerning the intercept, the population intercept. This is the t-stat. Test statistic follows a t distribution, and this is the degree of freedom, which is equal to n minus 2. And the standard error or the standard deviation of the intercept equals to root of 1 divided by the sample size plus the mean of the independent variable squared divided by this figure. Denominator is nothing but the numerator that we use in the variance of the independent variable. You need to remember the formula because you might be asked to calculate the standard error of the intercept. Section 6, which is prediction using the simple linear regression model. The ultimate objective of a linear regression model is to be able to forecast the value of the dependent variable using the forecasted value of independent variable. Suppose an analyst regresses GDP of a country against the short-term interest rate. So he wants to forecast what could be the GDP for the next year. So he forecast what could be the short-term interest rate for the next year, and using the forecasted value of the independent variable, he forecast the dependent value. So the forecasted value of the independent variable is denoted by xf, and the forecasted value of the dependent variable is indicated by y hat f. And this is the linear regression model for forecasting the dependent variable using the forecasted value of independent variable. And this is the simple linear regression model. The only difference between this model and the linear regression model we have seen previously, that here we use the forecasted value of the independent variable, where in the previous model we used the observed value or the actual value of the independent variable. However, we need to consider that the predicted value is not 100% accurate. The forecasted value is not 100% accurate. There is still some uncertainty. So instead of just forecasting one value of the dependent variable, it is advised that we construct an interval and conclude that the dependent variable's value could lie somewhere in between this interval. Therefore, we need to construct an interval estimate around the forecast. And this is the formula to construct the interval estimate. So suppose this is the forecasted value of the dependent variable. The upper side of the interval will be the forecasted value plus the critical value at a particular level of significance and against a particular degree of freedom multiplied by the standard error of forecast. And the lower boundary of the interval will be the forecasted value minus the critical value multiplied by standard error of forecast. Because it's a two-tailed test, so for a 5% level of significance, the critical value will be calculated using 2.5% level of significance for the right side and 2.5% for the left side. And the degree of freedom will be n minus 2. And the standard error of forecast is this formula. It is highly unlikely that you will be calculated or tested on this formula. Most probably, you will be given the value of the standard error of the forecast on your question. Now let us understand what is the standard error of forecast. Standard error of forecast tells us the average deviation of the forecasted value of the dependent variable from the actual value of the dependent variable. There is a subtle difference between the standard error of estimate and the standard error of forecast. The standard error of estimate told us the average deviation of the predicted value or the forecasted value of the dependent variable from the observed value or the actual value of the dependent variable. But the predicted value was calculated using a known value of independent variable. But here the predicted value or the forecasted value of the dependent variable is calculated using the forecasted value of the independent variable. So generally speaking, the standard error of forecast will be higher than standard error of estimate, because standard error of forecast also considers the uncertainty around the forecasted value of independent variable. Standard error of forecast considers the standard error of estimate. Along with that, it also considers the uncertainty in the forecasted value of independent variable. And the standard error of forecast is also influenced by the sample size n. So as we can see from the formula, larger the standard error of estimate, larger will be the standard error of forecast, and more the uncertainty of the forecasted value of independent variable. That is, larger the deviation of forecasted value of independent variable from its average value, larger will be the standard error of forecast, and larger the sample size, lower will be the standard error of forecast. Seventh section, which is the functional forms for simple linear regression. As we have said earlier, that for simple linear regression model to work, there should be a linear relationship between the dependent and the independent variable. But not every set of independent and dependent variable have a linear relationship. So, to use a simple linear regression, even when the two variables have a non-linear relationship, what we do is we either transform the dependent variable or the independent variable, or we transform both the variables. And when we plot the transformed variables on a graph, we find that the relationship between the transformed variables is a linear relationship. So, by transforming the variable, we have a linear relationship between the two variables, the two transformed variables. The three most used functional forms are the log-lin model, the lin-log model, and the log-log model. Over the next few slides, we will be looking at each of these forms in much more detail. Let us look at the first model, which is the log-lin model. In this model, we transform the dependent variable. We transform the dependent variable and keep the independent variable in its original form. By transforming the dependent variable, we mean that we take the logarithmic value of the dependent variable and we compare it or we plot it against the linear value of the independent variable. So in log-lin model, the dependent variable is in logarithmic form and the independent variable is in its original form, or we call it as the linear form. And this is the simple linear regression model, where we establish a linear relationship between the logarithmic value of the dependent variable and the linear value of the independent variable. So for example, an analyst is conducting a time series regression. He regresses the yearly revenue against time. So this is the dependent and this is the independent variable. And this is how the scatter plot looks like, where we take linear form of both the variables. As we can see that there is a non-linear relationship between the two variables, and simply establishing a linear relationship between the two variables won't give us accurate results. The linear relationship underestimates the value at some points and overestimates the dependent variable at some points. So instead of plotting the linear values, what we can do is, we can take the log of the revenues and plot it against time. And this is the scatter plot of the logarithmic value of dependent variable against the time. Here it is clearly visible that the relationship between the transformed dependent variable and the independent variable is a linear relationship. Let us actually predict the value of the dependent variable using this model and this model. Suppose I want to forecast the value of dependent variable when the independent variable's value is 4, that is at the 4th year. So using this model, value of dependent variable will be negative 287.61 plus 76.578 multiplied by 4. And the value of dependent variable is 18.702. The actual value of the dependent variable, the observed value of the dependent variable against the 4th year is somewhere closer to 100 or 150. But using this model, the value that we got is 18.702. Now let us see what is the value that we get using this model. The log of y equals to 4.7932 plus 0.1087 multiplied by 4. So the logarithmic value equals to 5.228. This is the logarithmic value of dependent variable. Now let us convert this logarithmic value into its actual or the linear value. To do this, we take exponential of 5.228 and the value of the dependent variable is 186.41. So the predicted value of the dependent variable is very close to the actual value. So this is how we use a log-lin model to forecast the dependent variable. We must be cautious when forecasting the dependent variable because using the simple linear regression model, the value that we get is the logarithmic value of the dependent variable. We need to remember to convert this to the actual or the linear value of the dependent variable. The slope coefficient provides relative or a logarithmic change in the dependent variable for an absolute or a linear change in independent variable. So in the previous case, the slope coefficient was 0.1087. This indicated for a 1 unit increase or a 1 unit decrease in the independent variable, the dependent variable's logarithmic value will change by 0.1087. And we cannot directly compare the log-lin model with the lin-lin model, that is our simple linear regression model that we used until now. We directly cannot compare both the models as the dependent variable is in different form in both the models. So by not comparing both the models, we mean that the R square and the F stat, we directly cannot compare R square and F stat with the R square and F stat of lin-lin model. The second model is the lin-log model. Here the dependent variable is in the linear form and the independent variable is in the logarithmic form. And this is the linear regression model where we establish a linear relationship between the linear dependent variable and the logarithmic independent variable. Let us take an example to understand this. Suppose an analyst is regressing the operating margin against the sales unit. This is how the scatter plot looks like, where on the x-axis we have number of units sold and on the y-axis we have the operating profit margin. Clearly, the two variables don't showcase a linear relationship. There is a non-linear relationship between the two variables. Now let us convert the number of units sold into their logarithmic value. And this is how the scatter plot looks like. When we plot the log of independent variable against the linear value of dependent variable, there is a clear linear relationship between the two variables. And this model does a great job of predicting the dependent variable compared to this model. Now suppose I want to forecast what is the operating profit margin when the number of units sold is 60,000. So against 60,000, this is the actual profit margin, which is somewhere closer to 16 to 16.3. So using this model, the profit margin that we get is somewhere closer to 13%. And using this model, the dependent variable equals to 2.6286 plus 1.1797 multiplied by log of 60,000, which equals to 2.6286 plus 1.1797, and the log of 60,000 is 11. So the dependent variable's value is 15.60. As you can see, the predicted value is very close to the actual value, which is somewhere between 16 and 16.3. So this is how we use the Lin log model to forecast the dependent variable. In a Lin log model, the slope coefficient provides the absolute change in the dependent variable for a logarithmic change in the independent variable. And because the dependent variable in both the Lin log model and the Lin model is in the same form, they are both in the linear form, we can directly compare R square or say the F stat of the Lin log model and the Lin model to find out which model does a better job of explaining the dependent variable. The third model, which is the log model. Here both the independent and the dependent variables are in logarithmic form. And this is the log model, where we establish a linear relationship between the logarithmic dependent variable and the logarithmic independent variable. So suppose an analyst is regressing revenue against the advertisement as a percentage of selling general and administrative expenses. So this is how the scatter plot looks like. Definitely the linear regression line doesn't do a good job of predicting the dependent variable. Now let us convert both the variables in logarithmic form. And this is how the scatter plot looks like. And here we can directly compare the Lin model against the log model. Even though the dependent variable in both the models are in different form, but we can still compare both the models. So the R square of the Lin model is only 20.89%, whereas R square of the log model is 85%, which is pretty good. So the log model does a great job of explaining the dependent variable. The slope coefficient in a log model provides the logarithmic change in dependent variable for a logarithmic change in independent variable. And even though the dependent variable is in different form in both the models, but we can still directly compare their R square and their F stat. So we have seen the Lin model, which is the simple linear regression model. We have also seen the log-Lin model, the Lin log model, and the log model. So among the four models, which is the correct functional form? Which form or which model should we use to forecast the dependent variable? So to find out which functional form to use, we examine the measures of goodness of fit. The model with high R square and high F stat should be preferred over other models, and the model with lower standard error of estimate should be preferred. For some models, we directly cannot compare the R square F stat or the standard error of estimate. In such case, we need to transform these measures of goodness of fit and then compare the two models to decide which model is more accurate. Along with the measures of goodness of fit, we should also look at the residual plot. If you remember that while discussing the first assumption, the linearity, we discussed that if the residuals are not random, then it implies that there is a non-linear relationship between the dependent and the independent variable. So we want to select the model whose residuals are random. This implies that the relationship between the linear dependent variable and the linear independent variable, or the transformed values of the variables, the relationship between them is linear. So we should look at both the measures of goodness of fit as well as the residual plot to decide which functional form or which model to use. An analyst is investigating the relationship between annual growth in consumer spending and the annual growth in country's GDP. So the GDP is dependent variable and the consumer spending is independent variable. We have two different models, and these are the regression coefficient and the measures of goodness of fit. The first question is to identify functional form used in these models. So the first model is a lin-lin model and the second model is a lin-log model. The second question is which model has a better goodness of fit. So model 2 has a higher R square, it has a lower standard error of estimate, and it has a higher F statistic. So all the three measures of goodness of fit are in favor of model 2. So model 2 has a better goodness of fit. Hence model 2 should be used to regress the GDP on consumer spending.